Hello everyone, I'm Monty Zwiebin. I'm the co-founder of Splice Machine and CEO. I've been working in databases for a few years now and working in artificial intelligence for many, many years. And I'm here to tell you about the architecture of the Splice Machine Relational Database Management System. And so why don't we just begin with a couple of quick questions. First, how many in the audience have used SQL databases before? Knew that answer. How many people in the audience use HBase? Good amount. How many people use Spark? Smaller amount. Great. That'll help me position the architecture and give you the proper level of depth. But the whole idea of what we tried to do at Splice Machine a few years ago is after going to one of the first Hadoop users group meeting, which is not much bigger than this. It was the annual meeting, and we essentially watched what was going on in the space, and we thought to ourselves, Hadoop is great. It's an incredibly disruptive architecture. I sit on the advisory board for the Dean of Computer Science at Carnegie Mellon University, and I remember him presenting the first MapReduce paper and how important it was going to be for computer science and the research all through the computer science department there. And I watched the space, and thought to myself, how are people going to write MapReduce functions in IT organizations around the world? How are people going to be able to take advantage of this incredibly powerful distributed architecture? And what we all thought at Splice Machine was that we've got to deliver the power of this architecture on a paradigm that everyone knows. And that was SQL. So we set out to build an operational SQL database on the Hadoop infrastructure. So unlike Hive, unlike everything else that is SQL on Hadoop, while we do analytics, we also can power applications. So it's a mixed workload relational database management system. It has full SQL capabilities. It's obviously a scale-out architecture. That's why we're here at a Hadoop user group meeting. And it's very fast compared to traditional relational database systems. And it's built on Hadoop and HBase, as well as Spark. By the way, has anyone in the room heard a Splice Machine architecture description? A little bit there, a little bit there. So not a lot of people. Okay. So it won't be that redundant. I apologize for people who heard it before. The business reason, and I'll blow past some of the architecture here quickly so that you can really see the architecture. Really what we're trying to do is help people get at their data in the moment. Being able to make business decisions in the moment is what we're all about. Being able to not look in the rearview mirror and wait for data from a day ago or a week ago, but actually being able to analyze data from moments ago is important to the digital marketing world. It's important to the healthcare industry to be able to look at electronic medical records and understand when there's a dangerous situation in a hospital. It's important in the financial services industry when you have to look at compliance data for securities that have taken place, security trades that have taken place in the day, fraud detection, and of course in supply chain optimization, being able to track every movement of the inventory and know exactly how that movement affects the overall supply chain. There's lots of applications, and today we simply did some simple surveys asking people how old is the data in their reports, and it turns out it's almost for everybody older than a day or two. So the reason for this is that the traditional operational database and analytical environment is rife with ETL. How many of you have dealt with ETL pipelines? Many of you. So you know the legacy of the latency in these legacy architectures. You know how long it takes to get data out of an operational relational database into some sort of analytical database. Whether it's Hadoop or a traditional MPP system or even an old relational database management system that's architected for analysis, this is just no longer adequate. So what people have done is, in recent years, if you look at today's most modern architectures, architectures here at Yahoo, architectures at Rocket Fuel, Google, Facebook, everywhere people are building Lambda architectures. And Lambda architectures is just a simple idea, which is essentially to use multiple compute engines for a particular task in order to compute different workloads. So you might take a streaming data source from Kafka and have an analytics layer on Hive and have a serving layer in HBase and a real-time calculations going on in Storm. But what's wrong with Lambda architectures is that it's up to you as the developer to glue these things together with duct tape. And every time one of these versions change, you have to change your versions, and it's hard to keep these data sources in sync. But at least with Lambda architecture, you don't have the legacy of that latency that comes from the operational system to the analytics system. You immediately have your analytics system getting access to the data. But there's a new approach, and it's the architecture that I'm going to tell you about, which is kind of putting a Lambda architecture in a box. In other words, using multiple compute engines for different workloads, but not exposing that complexity to the developer. So that's what I'll be talking about now. And the whole idea of this is by using multiple compute engines, you essentially are providing an isolation of resources for your transactional or operational workloads from your analytical workloads. Unlike the old days when OLTP transactions would get backed up behind heavy-duty OLAP queries, you now have free lanes for analysis to take place on one set of CPUs with an allocation of memory, and you have transactions taking place on another set of CPUs with allocated memory. So that's the idea behind the Splice Machine architecture, is resource isolation. And the whole idea is hopefully to be able to load up analytical workloads but not have an impact on your transactional throughput. Okay, so if you think about what we're trying to attack, it's both the old and the new. So we're trying to help organizations bridge the gap between their operational workloads and their analytical workloads by putting them on the same platform, removing the pain of ETL. And we're also helping the Lambda architectures of the world, the newer applications, by removing all that duct tape and making it much simpler to use multiple compute engines that are emerging to perform multiple workloads. So here's the architecture. So the architecture works in the following way. We started with 3 open source stacks. The first was a SQL system, a SQL relational database system that was built in Java called Derby. And we gutted Derby's storage layer and put HBase in to be the persistent storage of our database. And for analytics, we use Apache Spark. And I'll show you how that works in a few minutes. But the connectivity to our database is very traditional. You connect to the database with JDBC or ODBC, plus we have a batch import mechanism to be able to parallelize large ingestion tasks. And of course, you can stream data in as well. And we create in our parser an abstract syntax tree that then gets planned for access to the data. And then we optimize that with our optimizer, and then the optimizer decides which compute engine to use. I'll talk about this in more detail in a few minutes. So many of you raised your hands when we were talking about, when I asked you the question of whether you've used HBase. So just a 30-second review of HBase. HBase made data in the Hadoop file system mutable, meaning that you can change individual records without having to change whole files. It is a key value store. All the data is stored in sorted order based on a primary key. And it is a write optimized store. It's of course modeled after Bigtable from Google, where you write into a mem store. When the mem store fills up, it flushes out to disk and creates a file, which is then replicated on the Hadoop file system. And in the background, occasionally those multiple files are compacted back together. It's a very fast key value store. It's proven to be used at petabyte scale in many different applications. What we've done is integrate HBase and Spark in a very smart way. Instead of going through the HBase API, when our system decides to do an analytics query, it actually can grab the representation of any particular table off the HDFS files and create what are called RDDs in Spark. RDDs are the data structure that Spark uses to maintain large-scaled, in-memory representations of data across the cluster. Okay, so the architecture works in the following way. So you connect to the database, and you issue a SQL statement, and the system creates an abstract syntax tree of the SQL. It then creates an optimal query plan. It optimizes what you would expect a relational database management system to optimize. It figures out whether it should access the data table or an index table if an index exists. It figures out what join order to use if it's a very complicated join. And it picks which join algorithm to use. And there are many join algorithms. There are distributed join algorithms. And then it generates bytecode. And what the system does is it interrogates the statistics for the query and asks a question about how big any of the intermediary and final result sets are going to be. If the cardinality is larger than a threshold, then it will execute the query on Spark. If it's a very small query, it'll execute, as the slide shows, the transaction on HBase. And of course, if it's not, it'll execute it on Spark. The cool things about it is that the bytecode that's generated from the planner is executed, the same bytecode is executed on both architectures. And so I think I have a couple of slides. Let me go quickly here in the interest of time. Yeah, I want to go right here. There's a great deal of nice graphical user interfaces that I won't have the time tonight to go through, but using explain plans and the Spark user interface, you can interrogate what's going on in the database, see the plans, look at data that's being serialized and deserialized, figure out which node is doing what, and really figure out how to tune your database. But what I want to say is that one of the things that's really important for us at Splice Machine is to really build a full SQL database. And this isn't just for data science. We actually power applications. It's a full transactional database with commit and rollback. And I'll talk about the asset properties in a minute. It performs integrity constraint checks, foreign key checks, and things like that. It has full up stored procedures. It does triggers. It's got everything you need to power applications. In fact, people have ported their existing applications that run on Oracle to run on Splice Machine. And they're literally running applications, operational applications, on the Hadoop stack that used to work on Oracle. In fact, one thing I don't have a slide for that I really want to emphasize, that recently we announced a new capability, which is a PL/SQL capability. Does anyone know what PL/SQL is in the room? So that's the stored procedure language for Oracle. It's kind of an ancient programming language for those who might be programming in more modern languages, but it's probably got more code out there than everything other than COBOL, and it is ubiquitous all through IT organizations around the world, and it's what impedes the migration of workloads from Oracle to the Hadoop stack. So what we've just built is a PL/SQL compiler and executor. So your native PL/SQL can run on our database without having to rewrite that code. And so it's a pretty cool thing to be able to run somebody's very old logic on this stack without migrating their code. It reduces their risk, it expedites the transition from Oracle to Hadoop, And it's just a pretty cool thing. We're very proud of it. So very robust SQL capabilities, including operational capabilities. So the magic behind our application is that we built a full concurrent MVCC. MVCCs are multiple value concurrency control methods, and those are the techniques that are used by traditional databases to be able to maintain the ACID properties of the database, to make sure that all transactions are executed atomically, keep the database consistent, make sure there's proper isolation between the updates to the database, and make sure that once you write something to the database, it is durable, meaning it remains. The MVCC system that we have is improved over what HBase can do. HBase has some ACID capabilities. If you update a single record in a single table, it maintains the ACID properties for that particular update. But what we have done is maintained ACID properties across multiple updates, across multiple tables. So multiple records, multiple tables. And that's the intellectual property that we really are excited about. And that is what enables us to power applications. We built on previous research, and the previous research started with Google's papers on what was called Percolator. That was the transactional layer on top of their big table system. And then Yahoo actually built Ahmed and open sourced it. And we built on top of the Ahmed system, and in fact, one of the Ahmed leaders is one of the principal scientists at Splice Machine. So we're really excited about being able to handle very granular, very concurrent transactions. This is unlike Hive and unlike other systems that are massively parallel systems that have transactional capabilities that are more batch-oriented. Like you can take a big batch of data and make sure that it's updated atomically and do analysis on it. We're talking about millisecond updates with multiple concurrent people at the same time, literally powering applications. And since it's ODBC and JDBC, you can connect to it with all the traditional tools, whether you're a Tableau user or a MicroStrategy user, whatever you use to manipulate and visualize your data, you can integrate with our database. We're open source, and our community edition is unrestricted, meaning you can grab it, and I'll show you where to grab it in a second, from our community page, and you can perform any workloads you'd like on it in an unrestricted way. Any number of nodes, as much data as you want, there's no database feature per se from a SQL perspective that's missing from the database. However, we do also have an enterprise edition that we charge a subscription license for, including support. And what we've included in our enterprise edition are the ops features. So things like backup and restore, Kerberos, encryption, LDAP integration, column level access privileges, those kinds of things, and PL SQL. All those capabilities are in the enterprise edition for us. You can try this at scale really easily. Of course, you can download cluster versions off of our community site if you have your own cluster, but many of you may not have a cluster available, probably all being used. If you want to give this a shot on Amazon, we have a 5-click sandbox. You just simply specify your EC2 credentials, how many nodes you want to load up, what size node you want, and a couple of names. And we'll have CloudFormation templates that automate the provisioning of the cluster, loads up all of our software, and minutes later, you'll get an email saying your cluster is ready, connect to the database, and you can start issuing SQL. So I encourage you all to try it. There's also a standalone version. So if you just want to give it a shot functionally, not at scale, you can download a version to your laptop and just try SQL, connect up something to it, connect an app to it, run the app on it, or connect Tableau to it. Try that out. But all of that is available as a standalone, a cluster version, or an Amazon version. And on our community site, there's lots of code now. So if you want to figure out how to use machine learning libraries like MLlib and Spark and connect that up to our result sets and really make some AI applications very easy. We have videos to show you how to do that. If you want to see how to use Spark streaming and bring streaming data sets into Splice Machine to do IoT types of applications, we have videos for that. It's a pretty robust library of videos and little snippets of code that will help you accomplish your tasks of whether you're connecting to Splice Machine, integrating it to some other application, some visualization tool, or just wanting to perform some sort of computational task on it. And we do have a Slack channel that I'm very proud that our teams have been extremely responsive at answering on. So should you have any issues giving this thing a whirl, please don't hesitate to get on the Slack channel and tell people that you've had a problem. We really want to make this frictionless. We know that we're new to the open source community, just a few months. I'm sure there are little glitches here and there. We want to fix them. So let us know if you have any problems. Don't just hit a speed bump and quit. Just drop us an email or at least say something on the Slack channel. And of course, our source code's out there. If you want to see how this thing works, you can go right to GitHub and clone it. And what I'd really love is if some of you would join our community and fix some of our JIRAs and do some of the new features and essentially become contributors to Splice Machine. We have some great people around us, an advisory board that's really impressive. Roger Bamford, who is the architect of Oracle RAC, Mike Franklin, who used to run the AMP lab that created Spark, Marie-Anne, who founded Times10, the first in-memory database, Abhinav, who used to be at Yahoo here and then co-founded Rocket Fuel, built one of the largest HBase clusters in the world that's still live and running and serving ads using machine learning, and Ken Rudin, who is running search analytics at Google. We have a couple of new board members as well that we don't have slides for, and we'll just be announcing in the next couple of weeks, one of which is a president from SAP, and another one is the Dean of Computer Science at Carnegie Mellon. So we're hiring. If anybody wants to join our team and build this database technology, we're looking for people at all levels of the stack. And we've got a great team, and we really want you to give it a shot. Try it. Let us know what you think, and let us know how we can make it better.
Thank you, Marcus. Do you have any questions from the floor?
So how does the installation work if someone has a Hadoop cluster already with HBase running and Spark running? Is this going to leverage those engines that are already in place, or do you embed it and install your own? And is it going to co-locate in your Hadoop cluster, or is it a separate cluster?
That's a great question, and it's a little bit of a complicated answer, but our Spark is contained in Yarn, so it is a good cluster citizen. We don't recommend for people to share their HBase instance with us because it's really hard to do resource isolation in HBase. And so we really want to have a dedicated HBase instance for our installation. We do run well on a large cluster where we're just being installed on a subset of that cluster. And I think many of our installation scripts can help with that, but in more complicated situations, feel free to tap our community to kind of slip it into an existing architecture. But most of our install scripts will install based on the distribution that you're clicking on. On our community page, you can click on MapR, Hortonworks, and Cloudera, and it'll, for example, on Cloudera, create a parcel, and it'll be different for the different distros. Mic is necessary back there too, so
yeah,
we're the next person.
Do you have any benchmarks on how it is performing by size?
Yes, I do have some benchmarks. We just recently did something. I think we have some in here that might be hidden. I'm going to check and see if they're here. And if not, I'll tell you about it and we'll point you to some things later on. Yeah, it looks like it might not be in this deck. We recently did some interesting TPC-H benchmarks to compare and contrast against others that are building mixed workload systems. I don't have it there in the deck, I apologize. For example, we compared against Phoenix, which is the SQL layer on top of HBase, and we compared against Apache Trafodian. And we performed very, very well with, I would say in most cases, many-fold faster using our Spark architecture in those experiments, and we've posted those experiments at HBaseCon. Best place to look for those benchmarks is to go to the most recent HBaseCon in New York and see our co-founder and CTO's presentation, and one of our, in fact, the Ahmed scientist, Daniel and John's presentation at HBase has this comparison, and they point to the GitHub with these experiments so you can repeat them if you want to see if they're real or not, and see if you get different results. We'll be publishing TPC-C results and TPC-H results, and most importantly, what you'll see from us very soon is a published report of running TPC-C, which is the transactional workload test, and TPC-H simultaneously. We do that in our sales calls. We kick off those two benchmarks and run them simultaneously, which usually gets a big aha from customers because most people can't do that. And so that's an important benchmark that we can also publish for folks.
Yeah, we have a few other questions, but we'll go in sequence, I think.
Yeah. So my question is, how do the backup and restore? I know that's enterprise feature, and so this is like Oracle-like backup restore, or what is it?
Okay, so in fact, the developer of the backup and restore is right behind you. That's June right there. So if you have questions, June, raise your hand so you can ask him questions later. But backup and restore is, we can point the backup and restore to any file system, for example, to HDFS or to S3. With the way it works, loosely speaking, keep me honest, June, make sure I get it right, is that the backup takes the underlying structure of the persistent storage, which in our system are H files for HBase. It groups them together and then points them and basically points them out to where you want to put your backup. And then the restore takes that zipped together set of files and puts them back into the right place and invokes the right transactional context. So this whole backup and restore is important because it maintains transactional integrity. Did that answer your question?
So basically you're just using HBase, H files, but I'm talking about like incremental.
Yes, it's both. Great question. I'm sorry, I should have said that. So we have full backup and restore and incremental backup and restore. We have both. What we don't have, what features, and I think this is true, we don't yet have the ability to say, for example, just back up that table versus back up your database. And we'll have that soon too. That's a feature to come. Is that right, Jim? Yeah.
We have some questions from the back.
Hey, two questions. Number one, can you talk about the indexing strategy? How does that work? And also, what are the larger production deployments today out there?
So first, the question on the indexing strategy. We create indexes with transactional integrity. So the beauty of that is that if you update a record and there are multiple indexes on the table, we'll make sure that that update is done atomically with every index. And so that's an important element of what we do. We implement indexes as separate HBase tables. Important to note that in our system, this is a good time to note this, it's a detail, but it's an important detail. In Splice Machine, let's say you declared a SQL table that had 1,000 columns in it. The underlying representation in HBase would not be what you'd think is a straightforward implementation of that, of 1,000 columns. We actually have one column that's used for our values. We compress with an encoding that is a very condensed encoding so that we don't proliferate primary keys and make a very chatty database. Indexes work the same way. So for a table that has an index, every index is another table. And we typically use covering indexes too, so that we can avoid round-trip RPC hops as a best practice. So that's how we do indexes, but they look just like SQL tables. You just declare an index, a secondary index on any column structure you want, composite columns as well.
Yeah, I think we had two people somewhere in the middle, so we'll try to take these two as the last questions for the interest of time. I think he was before you.
Yeah, I've got two questions. The first one is which version of Spark are you supporting? Second is how do you, when you issue the Spark request, do you issue a request directly Spark execution engine or go to the SparkSQL? There's the SparkSQL.
Very good question.
The whole,
Yes, excellent question. So first, we have recently ported to Spark 2.0, so we're on data frames now, which is fantastic, and we're very excited about some of the power underlying Spark. In fact, when data is moving around in our current version of the system, in our tip of our GitHub, it's using the tungsten representation that the Apache Spark people use, which is a very cache-friendly binary encoding of data. And to your last question about how we dispatch the query, we do not use SparkSQL for the majority of what we do under the covers. We're issuing our own, we're just simply dispatching with parallelized types of operators on RDDs under the covers. Having said that, little by little, as Spark gets very efficient, we're starting to bring a little bit of Spark back into our system. For example, just recently, one of the developers checked in window functions that now use SparkSQL's window functions, which is they've done a very nice job on that. And what we will be checking in really soon is some of Spark's ability to read and write Parquet, and will be columnar in that regard. That's a coming feature, weeks away. Moreover, being able to leverage some of Spark's sort capabilities on tungsten representations. We'll be incorporating that very soon too, once they fix a bug with nulls and how nulls are handled on sorting. But so the general answer to your question is we dispatch work on RDDs using the Spark engine, not SparkSQL, but occasionally we use a little SparkSQL.
Hi, I wanna ask about the PLSQL optimizer native as well. For example, if there's a specific keywords, partition keyword or other maybe optimizer hints that Oracle uses specific hints, what it's like to
Excellent question.
or,
Yeah, so important to note that while we support native PL/SQL, I wouldn't want to claim that in our 3.5 years of being, a company and only a couple of years of having a product, do we support full Oracle SQL, right? Oracle SQL is a very robust language. So there's a good deal of SQL that Oracle, non-ANSI-SQL, we're full ANSI-SQL, but not fully Oracle SQL. So if somebody has a lot of PL SQL, there may be elements of that PL SQL that has Oracle SQL we don't support. And some of the keywords, for example, that you just mentioned are in those SQL that we don't support, like partition and as of and things like that. So our PL SQL system will catch that and issue exceptions, and we have an exception report, so that it makes it easy for people to do the port there. So, but one of the other things that's really cool is that it does all the data type conversion the way you would expect it to in Oracle. So the compiler really does execute PL/SQL, and all of the inferred conversions that take place when you don't declare.
Thank you very much, Monse.
Thank you.
One thing to note is Splice Machine has some goodies out there. So before you leave, please feel free to drop by the side desk. Folks from Splice Machine are there, and you can meet them up. So let's have a clap for Monte.
Thank you.